Assalamualaikum warahmatullahi wabarakatuh. For today's session, turn to page 394. So our subtopic 15.3, for example, here will be covering energy of the simple harmonic oscillator. So aside of learning about energy, we are going to look at another example of simple harmonic motion called pendulum. And then we are going to look at what happened when we now introduce friction. Recall in the previous video that for simple harmonic motion to occur, there should not be any friction. So in this video, we are going to discuss what will happen when there is friction. Finally, it will be covering on the concept of forced oscillation. So here we are looking at scenario called resonance. There are two types of energy that we are going to discuss. Number one is kinetic energy, which is half mv squared. Number two is potential energy belong to the spring. So we are going to look at this. Now, basically, half mv squared is a product of kinetic energy we have seen earlier. On the other hand, there is one additional energy which is called as potential energy, where we can calculate it by using half k times x position squared. However, the two energy simply vary with one another, meaning to say the total amount of energy is conserved. However, as object move to the right, to the left, back and forth, they interchangeably change the amount of energy between one another. But when you do the summation of their total energy, they should have the same amount. So without further ado, let's look as well at another expression. We call it as total energy. Now, so provided here that for a simple harmonic motion, if you did know the amount of amplitudes, then straight away you can calculate the amount of total energy of the system. Now, recall back what happens during displacement is at the amplitude, the largest value of x. You should find at that location the instantaneous v or speed at that location turns out to be 0. Due to that, there is solely only one type of energy, which is potential energy. In short, at this location x equivalent to a, energy is purely in the form of potential energy belonging to the spring. And that's the reason a product of half k a at a squared, half m squared, will give you the product of the total energy. However, there is another technique as well. If you did recall another version, when x now turns to be 0 at the equilibrium, you should find the v value at that moment will portray the largest value, or we call maximum speed. Hence, it's also correct to write down that the amount of half k a squared should be equivalent to mv. However, the v that we are interested of is the maximum speed. Now turn to page 396. We are going to see how the amount of energy changes between these two types of energy. We are talking about 1. Kinetic, 2. Potential energy belong to the spring. Here, there is no elevation, so there is no potential energy from the gravity. So at the location given as A, when the object experience A maximum, hence we are looking at displacement at the amplitude, you should find that the amount of energy of the kinetic energy is equivalent to 0 as portrayed here. And the amount of energy 100% are equivalent in the form of potential energy. Right, let's look at another version at D location. So D is where the positioning is at the equilibrium. The line here indicates its equilibrium. Look again at how the potential energy now turns to be 0. It's 0. Okay. Same thing with the acceleration. So the whole energy now is in the form of what we call half m, but the v must be maximum speed. So observe the amount of the maximum speed is equivalent to half ka squared. In terms of the expression might confuse you a little bit, but we are going to portray that the amount, jumlah dia, is the same as at the location of A. Jumlah mereka sama. So it's also correct to calculate the amount of kinetic energy at this location to be equivalent to a product of half ka squared. Okay, so if you don't have a V at this location, but the question is asking you what is the value of the K, yes, you can use the product of half K squared. The value substituted here at the end of the day will give you the amount required. Alright, in between them, when for instance it's not neither A neither 0, maknanya antaranya. So we find that the amount of energy still remain the same amount, or the red colour sama je bar dia 100% nilai dia, tetapi they are now divided into two. So some are being taken in the form of potential and some is in the kinetic form. So how do we write it when it's in this version? So we can write it in F, KIV. Have a look at this expression here. So you should find that whenever it's neither x equivalent to 0 nor x equivalent to A, you can choose this generic expression that a half mv squared, a general expression of V, plus half kx squared should be equivalent to half k amplitude squared. And again, remember that at any time you can modify the expression into two versions. It could turn to be half mv maximum equivalent to half ka squared, number 1. Number 2, or it could turn out to be half mv squared. I'm putting it without any subscript to portray that the v that you are going to substitute here is less than v maximum, and hence there is a sum in the form of potential energy, which this should as well be equivalent to half ka squared or half mv squared maximum. So that's how you do the variation of the expression. Now before we proceed, okay, the whole idea of the variation of energy just now, aside having it in the bar form, we can portray it in what we call as energy graph, as portrayed in here 395. So this particular graph B are plotting together simultaneously two types of graph, kinetic and potential of the spring. So which one is potential? US is the potential. Now, go back to the idea. Okay, here it has portrayed. The yellow represent the potential of the spring. So observe at the location where at the amplitude, it has the largest potential energy. And the same thing at the location here at the amplitude. While you find that the kinetic energy is in the other opposite version. So take note on this idea, how the energy are plotted. On the other hand, technically, what is the idea? If let's say you did know the value here of the energy bar, okay, so this is the location. For instance, we can just put any example. Let's say that this is 0.5. So at this 0.5, the amount of total energy is the bar pointed here add up with here. So you are to sum up the potential and the kinetic. Sorry, the yellow is the potential, add up with this one. So let's just put certain value here. So you should find here, because this is an example, so I just put it here. So this is 2 perhaps, this is 5. So U and K. So K is the blue, so K is 5. The U is 2 here. So adding them up becomes 7. This is the total amount of energy, and this is where 7 should be. Alright, let's turn to example 15.3. Now in this example, you are about to observe the usage of the expression you seen earlier. Half Ka squared, half mv maximum squared, or half mv squared plus half kx squared. Now, so let's look at the question and identify the keyword. So according to the question, there was this mesh, which is a card. It gets connected to a spring, and that spring has a constant which is 20 Newton per meter. So that, let's label that. So there is no friction. So obviously this is now a simple harmonic motion. Since it's a simple harmonic motion, we can use what the energy approach we seen earlier. So by using energy approach, which is half Ka squared, half mv maximum squared, or perhaps in the generic form of half kx squared plus half mv squared. The question is asking you calculate the maximum speed when amplitude is this much. So this is how you portray the expression, or you express the expression, that when x is at the amplitude, then it will be a total energy. This is total energy. And when you substitute V as the maximum, again, this is as well equivalent to the total amount of energy. However, the things that students love to make error, because this is in the unit of joule. So you must ensure everything is in the SI unit. So observe that 3 centimeter now should be in meter. The K is adhesive, and mass as well should be in kilogram if it's given in gram. Okay, so this is the final answer we are looking at. Now, let's see if now you were asked to get the velocity or perhaps even the speed. When now position is 2 centimeter. What is 2 centimeter? Given earlier, amplitude is a product of 3 centimeter. So 2 is neither at 0, neither at amplitude, in between them. So go to the generic expression, that half K A squared is equivalent to half mv squared half K x squared. Now, you do not need to memorize it in this version. You can just go with these expressions because you already identify at this location of less than amplitude, there are two types of energy. Number one, potential. Number two, kinetic energy. And your aim is to get what is this value. So in correlation to that, just substitute all the proper number. So the mass earlier is 0.5. Amplitude earlier is 0.03, so squared. K is as given earlier, which is 20, and X is now this 2 centimeter, which should be in the form of, again, meter. So again, recall it should be in the SI unit. So you are looking at the answer because this is V squared. When you solve or rearrange the expression, yes, it has positive or negative, but for the final, perhaps this question should be in the version of speed. Okay, so it makes more sense for you to indicate, for you not to indicate the direction. Now, the next one, compute kinetic energy and potential energy. So let's do the calculation. The potential energy would be dependent on your previous V. So basically, get your calculator, try to punch it into your calculator, you will arrive with this number. Half kx at the 2 centimeter just now will arrive with this one. Therefore, if you add them up, then you are going to get 9 to the power of negative 3 joule. And this is we call as energy total. And because that is the energy total, it's quite interesting if you go with another version. Let's say that take again your calculator, calculate by using half k and then substituting 0.03 squared, you should arrive with the 9 just now to the power of negative 3 joule. So that's basically overall idea what it meant by the energy total and how we substitute into question. Okay, let's move further. So comparing simple harmonic motion with uniform circular motion. In the first video, we have seen this concept. So for this version, we're going into deeper and determine what we call as phase constant. So what is phase constant? So earlier you are given a generic expression similar as 15.23, whereby there is this additional expression plus phi, or we call it phase constant. Now the situation is we are going to use this quick quiz to explain how we arrive with that conclusion. Now, in the scenario of figure 15.13, that ball moved in a circle of radius 0.5, and this 0.5 at time 0, the ball is located on the left side, exactly opposite as in the position of 15.3. So the question is asking what will be the value for amplitude and the phase constant. Right, I'm gonna get it straight away. Number one, the amplitude is exactly equivalent to the radius and the phase constant is 5. So our issue is why is that? That is the answer. So let us go back to the figure of 15.13. So here is a scenario where a vertical turntable berputar, and at the edge, dekat circumference, we attach a small ball. The aim of putting the ball here is because we are going to illuminate a lamp light from above, from the top, and there will be shadow cast on the screen. So obviously as this one turn around, you should find as if the circular point belonging to the beads, belonging to the ball, belonging to this round blue object will appear to be moving back and forth, back and forth. So that is among reason why in the graph or in this equation we make use of the omega. Now another version, according to this question, it says that at the t equivalent to 0, it's on the left side. Okay, on the left side. So this is here. Okay, alright. Okay, not here. Okay, so this is where it starts. So this is the radius. Observe that the movement occurred from here to here and then goes back and forth, back and forth. So in short, here is the equilibrium at the center. So really conveying that at the axis of the rotation, titik tengah dia, center of rotation, is the equilibrium. And that's why it makes sense that the radius is the amplitude, the largest displacement. The largest displacement. Faham kerana paling jauh dia berada daripada equilibrium. So radius dia begini. Okay, now. So when we jot down in terms of the 5, okay, or perhaps we can start learning how to draw the graph itself. So the graph will look something like this. At t equivalent to 0, it's the positioning is on the left side. So this is displacement. So the left side meaning that it's here. Okay. And then a quarter after that, a quarter maknanya dia bergerak kan dari sini from here to the left, goes to the right and then go back to the left. Jadi at halfway, 1/4 after that is at the equilibrium. So kita pun jot down at the equilibrium lah. Okay. After at the equilibrium, masa tu 1/4 tu meaning that dia 1/4, I put it as period lah ya. T/4 dia. And then afterwards, they go to positive A. So positive A is here. Okay. So when this happen, this is at T, sorry ya. Okay. This is at T divided by half. Alright. And then what happened after that? It get back to 0, right? Okay, we can now complete the whole scenario. So it should look something like this. If we join all the lines, we are going to get one large cup, but in the version of inverted cup. Okay, within one, so this is where it ended. So one time, so it get back to the negative amplitude earlier, or negative R just now. Okay. So how does, go back and ask yourself, cos graph, how does it looks like? Cos graph, how does it looks like? Alright, so cos graph, you can have it like this. Observe, yeah, I'm gonna use this color, I hope. You see this? Okay. So a graph that belong to a cos is very similar if, okay, and then we get it to be continued. Okay. So what we are seeing that if we take away this, okay, we take away this, then we get the cos. So another technique that I'm showing you here is you can minus pi. Okay, you can minus pi. So there is another version as well. Okay, why? Okay, before we proceed, why is it that it's pi? Now, the whole thing occurred as such, and then get divided and we throw away half of it. The whole cycle is for one period, 1t, it should be equivalent to 2 pi in terms of the angle. Therefore, taken away, so this is actually angle. This is angle. Okay, angle. So taken away half of it would be equivalent to the pi. So yeah, it's minus pi. Now another way of to do this, it's also correct if some student observe that it should look something like this. I don't see it that way, madam. I see that that it should look something like this. I'm gonna, yeah, something like this. Okay, so it's actually correct to write down as well this version. Okay, so that you still end up with the shape of the cos, okay, at t0. Now that we have seen that the value of phase constant is pi, okay, we are now going to look at example 15.4 and substitute into expression, where in that expression we will find that we are not choosing plus pi. Okay, for what reason? Because of the movement. Because of the movement, in this case it's the right. Okay, so accordingly, the same figure is used and it's rotating counterclockwise. Radius given now changes to 3 meter. So this is your new amplitude with constant angular speed. Terms angular speed, angular frequency, both are referring to omega. Now, when it is at t, the shadow has a coordinate or position 2 meter. So, this is the x at times equivalent to 0 and they are on the way to the right. Determine the x coordinates of the shadow as a function of time. So, they want you to create the expression versus t, displacement or position with t. So with that, you should start with the generic expression that A cos omega t plus 5. And now, what's happening is, you are going to find what is the value of phi by substituting t equivalent to 0. And during that time, x is known position as 2. And while amplitude is given as 3. So when you simplify and try to solve, okay, again this is 0. So solve, you are arriving with this value. Now, something to ponder and recall whenever you are dealing with the process. Yes, radian mode. Okay, so arriving with this answer, okay, it's a plus and minus. Okay, it's a plus and minus. The key word that we are going to look at is by saying that the system is moving to the right. Okay, now where the effect that it moved to the right is this one, minus. Okay, so mathematically, if we substitute it to be a negative, then the plotting would be quite similar to our plotting earlier. Mathematically, every position will correspond and give a similar curve as this one. Alright, so that is how it works. If it moves to the right, then go for the negative. You minus it. Throw away this portion. Okay, throw away this portion. And whatever left behind, that's how you get the x. You get the expressions. Okay. Now that we are able to jot it down, okay, by getting A into the expression and also getting the 5. This is A, this is the 5 just now. So the next question is find the components of x in terms of the velocity and acceleration. So remember earlier that it should be having a generic expression of sine omega t plus minus 5. Alright, so just substitute it accordingly. If it's not asking you to differentiate, so you do not need to show a proper way to get and arrive to this expression. So you can quickly use this expression. Use saja, guna terus. So substitute A, substitute omega which is 8 tadi, angular frequency, angular speed, benda yang sama ya. And accordingly, so you have the generic expression for V and then as well for the acceleration. Faham ya? Guna rumus dia sahaja, masukkan. And that's about it. Alright, let's look at the second last subtopic, which is the pendulum. Now, in this subtopic, this is the version whereby we are going to arrive with what I mentioned earlier, where when you measure the period, you will arrive with an expression, I call it as talak. Period 2 pi square root L over G. You find that mass and K is not in the expression. So in this second model of simple harmonic motion, there is a limitation when it swings, not that all angle suitable and makes it become what we call as simple harmonic motion. Okay, before we arrive to that conclusion, something to ponder as well. When you swing, okay, it will oscillate back and forth, and the oscillation occurred because of what we call a components of gravity in the direction of the dot path. Now, along the dot path is where the displacement occur. So if somebody is asking you what is the restoring force, the answer should be lie to the component of mg here, which equivalent to mg sin theta. So mg sin theta ni adalah restoring force. Okay. So mathematically, I'm going to skip first in terms of how we arrive with this one. It's not that all angle will give you a simple harmonic motion. Okay. It should be, but according to this book, it should be less than 10 degree. If it's bigger than that, you will find that it will not exhibit simple harmonic motion. And because of that, you can use talak, the expression to get period for pendulum just now. For instance, why is it as such? Because you will find when you go with the product of sine 10 degree, okay, because of mg sin theta, it's equivalent to 0.028. Okay, so here there is another version whereby it tried to say when it's a less than that approximation, you find the product of sine theta is almost equivalent to the theta itself in radian. I repeat myself, yeah. So showing you that 10 degree divided by 360 degree and then sine it, you find equivalent to 0.028. But 10 divided by 360 degree will arrive with the same thing as well. Alright, let us continue from the idea of sine theta equivalent to theta, that in order for it to be simple harmonic motion, then it should be equivalent. Yeah, the angle must be small enough so that this is observable. So from there, the most important thing is we are to make a conclusion that period of a pendulum, which is equivalent to 2 pi over omega, okay, is also equivalent to the, or 1 over f, okay, is equivalent to talak. Okay, talak. Now, what is L? L is the length of the pendulum itself, and G is the gravitational acceleration value. Oh, it depends on the gravity of the earth. Okay, not mass, not spring. Okay, now let's look at this example. 15.5, a connection between length and time. Now, in this example, we are about to learn the whole idea of a clock, okay? And we would like to make adjustment to the length of the pendulum which used to make the clock, okay? So the question says that, by the way, in this question as well, there is an approximation. Observe that the technique used by this example will not be applied for our exam. For our exam, it will be much more precise. Okay. Now, the study is about this clockmaker, which is Christian Huygens, suggested that international unit of length should be defined as the length of time based on the period, which is exactly 1 second. So the question is, how much water would our length would be if we did follow his suggestion? Alright, so in the scenario given, as it swing pendulum, they swing back and forth. So if it start on the left side, okay, it should end on the left side as well, and the whole time it takes should be 1 second. So to estimate that, we get the expression of talak just now. Substitute T to be 1 second. Observe that T should be in unit second, yeah, not milli, not centi as such. So L remain an unknown value and G is 9.8. So solving, we are arriving with 0.248 meter. Now, in terms of discussion, so meaning that we should use a length of equivalent to 0.248 meter to replace the SI unit that we've been learning or using now. However, something to look at in different view, it should be less than 1/4 of its current length. So the whole length should be less by this one. So should be minus with this number. Okay, so then only the time would be defined as 1 second. Now let's turn to your problem of chapter 15, question number 17. So you should see this question. So a simple pendulum make 120 complete oscillation in 3 minutes where the location of G is 9.8 meter per second. Find period. Okay. Now how do we get the period? The period is not based on the expression because there is no length given. If we tend to jot down T, okay, T is talak, square root, L over G. We have partial data here. We don't have this L value. In fact, the next question is length. So we are not yet to use this expression. This is meant for B. So to get period, it should come from this 120. So go back and recall what is a period. Period is time. So time for what? Time for one oscillation. However, given in this question is the number of oscillation is 120. Meaning to say, period is time. Time is 3 minutes, but we need to convert into second for one oscillation. Then divide with the number of oscillation. Barulah kita dapat berapa masa yang diperlukan untuk satu oscillation, untuk one complete oscillation. Alright, now that you have that, only then you can go here and calculate the length required. Just to partially solve this, the G is 9.8 meter per second, and from here, please solve the value of the length. Okay, and unit is in meter. Alright, give it a try. Alright, 15.6. This is our last subtopic, which is damping. Now, in this subtopic, we are going to see introduction of friction and effect that when we have friction, non-conservative force, so system will be losing energy. So losing energy is it says here diminishes in time. So energy dia hilang. Why did the energy hilang? Because damping overall akan effect pada amplitude. Why amplitude? Okay, recall back that energy can be calculated by half kx squared. But I'm gonna focus on the total energy, which is half Ka squared. So when you damp kan, it's as if macam you reduce the value of A. So effect that A is now reduced, effect to the whole energy get reduced as well. So term diminishes in time is actually reduction, makin mengurang. Okay, we need damping. Why? There are a lot of damper, okay, for instance in cars, in motorcycles. So whenever the vehicles come across any bumping, we would like to reduce the effect of the bumping. Okay, so this is a scenario whereby on the bridge itself, there was a pair of spring loaded structure. Okay, so that it's become safer, alright, when it swing. Okay, alright, now so coming back to the idea, when we talk about damping, we need to identify three category of damping: under, over, and critical. Okay, now that we identify, we need to know how to draw. Okay, let's start with critical. Critical is the one which is the red color. Red color. So what makes it critical, or perhaps I should say the best, it goes to the equilibrium quickly, the fastest. So for T, for critical, T is the smallest. Okay, the smallest to come to equilibrium. Keyword there, ya. Over the other two, under and over, under represent that less friction. Friction kecil. Friction kecil. Effect that friction kecil meaning that the system able to oscillate. Senang cerita macam ni, the idea is kita nak the system when it goes and hit a bump, it stop. Kita tak nak the displacement or the disturbance just now create a scenario where the bumper is already 1 meter away but the car is still vibrating. So we want to stop all sort of vibration to the car. So with that in mind, when it is under them, so the car simply cannot stop oscillates. So you observe there's still vibration, still oscillation, okay, after some times. But over on the other hand means extra force, okay, extra friction. So extra friction allow it to go to the equilibrium, but the longest time, the longest time, okay, yang paling besar sekali. So in overall, how you distinguish the graph, the bentuk graph adalah in terms of the times and also a few oscillation it makes. Okay. Alright, 15.7, forced oscillation. In this subtopic, we are going to observe the resonance. How did that resonance come into place? Because there is a driving force, and that driving force match the natural frequency of an object. I repeat, what is resonance? Resonance is the effect when the displacement becomes the largest, okay, or it will swing with the largest amplitude. Why is it happening? Because the driving force is equivalent to the natural frequency of the object. Okay, so as we seen in this figure of 15.23, when frequency or angular frequency here, it tried to correlate the idea of F actually, equal with of the driving force, equal the natural frequency, then you should observe amplitude gets larger. Okay, and that's what makes this figure shows a Tacoma, okay, Tacoma bridge, where in 1940 the bridge happened to have vibration because of the swing. It swing because of the wind. Okay, but somehow on that particular day, the wind becoming driving force matches the frequency of the natural frequency belonging to the bridge. So what happened is the bridge swing to the maximum amplitude, and being its rigidity, maknanya dia keras tapi you paksa dia untuk bergerak, okay, it just collapse ataupun dia patah, in this case, so collapse, runtuh lah. Okay. Alright, so keywords of this topic is natural frequency when matched with the driving frequency. Then you will observe resonant. And what is a resonant? The effect where amplitude will be amplified.